redo that lesson because for some reason it wasn't showing a screenshot for the opening video. So just going to redo the whole lesson, but I don't expect anybody. So there's no need for anyone to tune in. This is just a repeat because the first 5 minutes. So this 11.4, we're going to be focusing on using first chain rule. Now we've already used this a little bit in 11.2 when it was just like AX plus B form. This is just going to be a little bit more complicated. So the first few examples here are where Lund's getting involved. Okay, so just to remind you from the differentiating point of view, you're differentiating A equals Ln of x function, then the differential rises the differential itself divided by the initial function. So for example, you've got y equals x squared plus 1. The differential of that is the differential of x squared plus 1, which is 2x, divided by the function itself, which is x squared plus 1. So looking at example 8 part A, therefore if we're integrating 2x over x squared plus 1, then clearly our integral is squared plus 1 plus c. So there's been no need to do any adjustment here because the differential of x squared plus 1 is exactly 2x. Now, more likely to crop up is where there's some little tweaking you need to do. So take example 8 part B. So our starting point with our side working is to take the denominator. So let's let y equal Ln 3 plus 2 sin x. Now when we differentiate that, our numerator is the differential, which is 2 lots of cos x over the function itself, which is 3 plus 2 sin x. Now clearly, looking at it the other way around, we don't want to be integrating 2 cos x. Want to be integrating 1 lot of cos x. So our adjustment here is a half here and a half here. Obviously the half and the 2 cancel out. So when we go and integrate cos x over 3 plus 2 sin x, we get a half of Ln 3 plus 2 sin x. Now, example 9 is when we're moving away from Ln being a factor, and we're now just looking at proper composite functions. So our starting point is always going to be, with our side working, to increase our power by 1. Okay, so we're going to go up a power. So in this situation here, where we've got sin squared x, our starting point is to consider y being sin cubed x, okay, which is obviously sin x cubed. Because when we differentiate, remember how the chain rule works, we multiply by the current power, reduce the power by 1, and multiply by the differential of the bracket. So that gives us 3 lots of sin squared x cos x. Now with this particular question, that's exactly what the question is. So there's no need for an adjustment with 9 part A. When you integrate 3 sin squared x cos x, or 3 cos x sin squared x if you like, you get exactly sin cubed x. So the integral of this is sin cubed x plus c. Now, part B. Again, a standard question. Our starting point with our side working is to increase the power by 1. So we're going to start off with x squared plus 5 to the power of 4. Now, using the chain rule, when we differentiate that, we get 4 lots of x squared plus 5 to the power of 3. Multiplying by the current power, reduce the power by 1. And then you multiply by the differential of the bracket, which is 2x. So 4 lots of 2x is 8x. So that's 8x multiplied by x squared plus 5 all to the power of 3. Now, we want to integrate just a single lot of this, not 8 lots of this. So our adjustment is to multiply through by an 8. So an 8th here and an 8th here. Obviously, the 8th and the 8th cancel out. So when we integrate x multiplied by x squared plus 5 to the power of 3, we get an 8th of x squared plus 5 to the power of 4. Now, example 10, just a little bit more complicated. As a starting point, let's take the denominator upstairs to make it to the power of -3. And so our starting point is still to raise the power by 1. So -3 becomes -2. So our starting point is let y equal 2 plus cot x to the power of -2. Then when we differentiate that, we multiply by the -2, then the bracket, reduce the power by 1, and then you multiply by the differential of the bracket. The differential of cot x is minus cos x squared x from down here. Okay, -2 times the minus over here is giving us a +2. So we've got 2 lots of this, whereas our actual question is a single lot of this. So our adjustment is a half here and here. So when we integrate this, we actually get a half of 2 plus cot x to the -2 plus c. Now, all the questions we've looked at so far, our starting point is to increase the power by 1. And you're always going to do that as your starting point, but you'll see occasionally that it's not appropriate, okay? And I'll show you why with this one. So with this particular question, we're not going to increase the power by 1. Our starting point is going to be to keep the power as is, okay? Now, you wouldn't have spotted this. You would have gone and increased it by 1. It wouldn't quite have worked, and you would have gone back and tried it this way. So this would be like your attempt number 2. So when we go and differentiate sec x to the power of 4, we get 4 lots of sec x cubed, multiplying by the power, reduce the power by 1, and then you multiply by the differential, and this is why the differential sec x tan x from down here. So that's actually introducing another sec x. So there we're getting a sec x to the power of 4 through this. So hence why we didn't need to go and increase the power by 1. Okay, so that's it. So I now want you to do exercise 11D. We've got 3 lessons this week, Monday, Tuesday and Wednesday. So I'm really thinking today and tomorrow, Monday, Tuesday, you work your way through exercise 11D. So tomorrow's lesson won't be live. And then on Wednesday, we'll meet up again and I'll talk you through integration by substitution.